Hello everyone and welcome to today's lecture, always in the same chapter in forming engineering materials from the elements. We will see the solid state. So here is an example of a crystal. Generally atoms in a solid are arranged in a regular array that is called a crystal. And in crystalline solids, the constituent atoms are organized in a rigid three-dimensional regular array known as the lattice. So here we have sodium ion, and in the green we have chloride ion. We have here the amorphous solids. So generally solids that don't have atoms arranged in a regular array are called amorphous solids, and these are example of amorphous solids. For example, we have the rubber, the glass, and the plastics. So based on spatial arrangement of atoms, we have crystalline materials and non-crystalline or amorphous. So the crystalline materials are particles that are arranged in a periodic array, for example metals and ceramics, and non-crystalline or amorphous are particles that are randomly distributed in space, like glasses and polymers. So we have here the unit cell and the lattice, and the properties for crystals are affected by the type of crystal structure, the grain size, and the bond strength. We have here the diamond and the graphite. Here is another example for polycrystalline solid. Here are the grain boundaries, and these are the unit cell orientation in grain A, and this is grain B, unit cell orientation in grain B. This is another demonstration. So this is the lattice, basis, and motif, and this is the crystal structure. Another one. So here are some types of we have the cubic, tetragonal, orthorhombic, hexagonal, monoclinic, and triclinic. These are the shapes of everything, and this is the trigonal. And there are 4 types of unit cell. We have the P for primitive, I for body-centered, face for face-centered, C for side-centered, and we have 7 crystal glasses and 14 Breve lattices. These are the demonstrations of primitive cubic, body-centered cubic, face-centered cubic, and simple cubic, body-centered cubic, face-centered cubic here. So 8 corners, and here we have 6 faces and 8 corners. So these are some basic structural parameters. We have the lattice constant or side of cube. We have number of atoms per cell. We have the volume per cell. We have the radius of an atom and the theoretical density. This is an example of Na plus and Cl minus. So bonding in solids are either strong or weak. For the strong state, we have the covalent, ionic, and metallic. The weak one, we have van der Waals and hydrogen. So these are examples of strong bonds, covalent bonds, and metallic bonding. We have here the ionic bonding as well. This is another example of weak interactions for the van der Waals bonding and the hydrogen bonding. So for the atomic bonding, we have some metallic bonds that are metallic elements that have electropositive atoms that donate their valence electrons to form a sea of electrons surrounding the atoms. And most pure metals are good electrical conductors of electricity at relatively low temperature. It's lower than 300 K. And also we have metals that show good ductility since the metallic bonds are non-directional. For the ductility, it's all about the ability of materials to be stretched or bent without breaking. This is another example of metallic bonds. So concerning the covalent bonds, they are materials with covalent bonding, and they are characterized by bonds that are formed by sharing of valence electrons among two or more atoms, and also a directional relationship is formed when the bonds between atoms in a covalently bonded material form specific angles depending on the material. And also covalent bonds are very strong, resulting in materials being mechanically strong and hard. For the covalent bond, we have the silicon atom and the covalent bonds. For the ionic bonds, it's all about when more than one type of atom is present in a material. One atom may donate its valence electrons to a different atom, filling the outer energy shell of the second atom. And the atom that contributes to the electrons is left with a net positive charge. We have the cation and the anion. So the anion is when the atom accepts the electrons, requires a net negative charge, and the oppositely charged ions are then attracted to one another and produce the ionic bond. So now we have the van der Waals bonding. When a neutral atom is exposed to an internal or external electric field, the atom becomes polarized. So this creates or induces a dipole moment. And in some molecules, the dipole moment doesn't not have to be induced, and it exists by virtue of the direction of bonds and the nature of atoms. So normally these molecules are known as polarized molecules. So they are also secondary bonds, but the atoms within the molecule are joined by strong covalent bonds. We have three types of van der Waals interactions. We have London forces, dipole interaction, and the Keesom interactions. For the London forces, there are interactions between two induced dipoles. For the dipole interaction, it's all about the interaction between an induced dipole and a molecule that has a permanent dipole moment. For the some interactions, they are interactions between molecules that are permanently polarized, and this is also known as a hydrogen bond. This is a quick illustration of London forces. So these are polarized atoms that attract each other, and this is a polarized atom that has a net dipole moment. For the qisom interaction, we have here the oxygen and the hydrogen. For the mixed bonding, it's all about the compounds that are formed from two or more metals, and it's called intermetallic compounds that may be bonded by a mixture of metallic and ionic bonds, particularly when there is a large difference in electronegativity between the elements. And the fraction of bonding that is covalent can be estimated from the following equation. We have the fraction covalent exponential of minus 0.25, and this is the difference in electronegativities. So here we have the binding energy and interatomic spacing. The interatomic spacing is the equilibrium distance caused by a balance between repulsive and attractive forces, and the interatomic spacing in a solid metal is approximately equal to the atomic diameter, or twice the atomic radius. We have the binding energy, it's the minimum energy required to break the bond. We have the modulus of elasticity, that is the slope of the stress terrain curve in the elastic region, and we have the yield strength, that is the level of stress at which the material begins to permanently deform, and finally we have the coefficient of linear expansion, that is denoted by A. This is the equation where L is the length and the T is the temperature. This is another figure of the interatomic energy. This is another figure as well, where we have the force and the distance. This is strong bonding and weak bonding. Another one of interatomic energy, where we have the equilibrium spacing between atoms.